Okay, and so we were in the middle of proving this theorem, which says it's this theorem on bounds on the support of vorticity with a Lipschitz continuous background vector field. Okay, and let me just do something here. Okay, and so this is the program. We've done most of this. We'll finish today. And so we proved a bunch of lemmas. And which we'll recall as we need them. And so I think at the end of the hour, we embarked on the proof of the theorem. And so oh no, I guess we're still proving this last lemma. Okay, so this is the last lemma. And so to remind you, we're looking at the growth in time of this quantity mu sub t of r comma h. And so this is, what do we do here? We take a test function who's 0 within a ball of radius r around the center of vorticity, 1 outside a ball of radius r plus h around the center of vorticity, and then transitions smoothly between them. We multiply that by the vorticity. And so roughly we're looking at the vorticity outside. So r and h will be of the same order. We're looking at the vorticity outside the ball of radius r around the origin. Think of r as being small, power of epsilon. And we want to know how that grows in time. And so the main claim is a differential inequality for the rate of growth in time of this smoothed out vorticity outside of ball radius r. Okay, and here's what we're trying to prove. We've started this, and so we began by, we did this last time. We differentiated this function u sub t. We used our general formula for the derivative of a test function multiplied against the vorticity. We broke into two pieces called an A1 and A2. I may have changed the notation since last time. So A1 is the term involving the velocity of the center of vorticity, and then the contribution from the forcing term, the background flow. And then A2 is the term from the velocity field generated by the vortex. Okay, and so A1, I think we did this last time. We used one of the earlier lemmas. So A1, when we recall our formula for dp dt, then A1 involves something of this form. And there's a minus sign missing, I believe. It doesn't matter. And then we use the earlier lemma, and we get something like this. Right, this is what we get, I believe. And okay, good. And so then let's look at A2. So A2 is here, and A2 is going to be handled by the other lemma from before. Let's see, what was A2? Here it is. The integral of the gradient of this cutoff function evaluated at x minus p epsilon. And then we take the dot product, I think, with this kernel, the VSR kernel of, well, yeah, let's write it out. It's x minus y orthogonal divided by 2 pi modulus of this x minus y squared, omega of x, omega of y, dx, dy. And then we look up here, and we can see up to this factor 2 pi, this has exactly the form of the one of the last lemmas we proved on yesterday, which concerns expressions like this, where we have a vector field G, a vector field G who vanishes in a ball of radius r around, who vanishes in the ball of radius r. We're going to evaluate G at x minus p, so it vanishes, so this G vector minus p vanishes in the ball of radius r around the center of vorticity. And G is a purely radial vector field, which is clearly the case here because we chose our chi to be a radial function. And so the gradient curve chi points outward. Okay, and so then we can just immediately appeal to the above lemma to find that this is A2 is bounded by, well, I'll just recopy this stuff. And let's see, what was R here? Right, R has the same meaning as above. Sorry, this is, so I'm just recopying this. Not much point, really. And so here M of R is the vorticity outside the ball radius R on the center of mass, and this I of omega is the second moment, which for us is always going to be small, like over epsilon squared. Okay, and so then we should simply obtain the conclusion of the lemma by combining these estimates. And so, right, so everything we see involves this. There's a factor of M sub T of R multiplying everything. That's here and there. We can see that. And then right, and there's also a right, there was an I of omega epsilon here. And so we also get terms involving constants, say the Lipschitz constant over R squared multiplied by this I of omega epsilon. So there are things which are multiplied by this second moment and therefore small. And then this last term has R times L over H. And so that will be at least bounded, I guess, if R and H are comparable. Okay, so in short, this just follows from the things we proved earlier. Okay, good. Now we should be ready to prove the theorem. But you can see the main point is, so earlier we did all these, we computed, well, okay, let's, what we're really doing is we're estimating, we have, imagine a particle trajectory for this Euler equation with the background flow. And so ordinarily particles just move by the velocity field given by u. That's how the particle trajectory map is defined. With the background flow, they move by the particle trajectory map given by u plus f. And we want to know how a particle trajectory for the flow, we'd like to ask about the distance from that trajectory and the center of vorticity. And so the things we estimated were all pieces of that. So there's the contribution, the outward radial distance generated by the vorticity, and at least generated by the part of the vorticity near the center of vorticity. And then there's the part driven by the difference between the flow of the particle along the vector field f and the flow of the center of vorticity, which is given by a kind of average of the vector field f over the with respect to the vorticity. Okay, so then let's see if we can. I guess I gave myself too much room for this. So okay, so finally here's the theorem. Bounds on the support, and I'm just restating this from before. Bounds on the support of vorticity if we have a Lipschitz background. And so same PDE, Euler equations where the velocity u is replaced by u plus f. F is Lipschitz with Lipschitz constant L. And our assumption is that the initial vorticity is contained in a ball radius epsilon around some point x naught, which is, we'll set that to be equal to, we'll set that equal to the initial center of vorticity. And we assume also that there's some, we assume that the, we just have some bounds in some LP space bigger than 2, that the growth in norms is no bigger than some negative power of epsilon. That's a pretty generous assumption. And so then the claim is that if we look at time t, so I fix some capital T, and what I would like is, and I fix some alpha, and this is an alpha less than a half. And the claim is that the vorticity is contained in a ball of radius epsilon, the alpha, so a bit bigger than square root epsilon, around the center of vorticity for all times from 0 up to time capital T, if epsilon is small. And so there exists epsilon depending on these other parameters, alpha and capital T, and so on, such that this holds. And so here again, this p epsilon T is the center of vorticity. Okay, let's see if we can prove this. And we'll need a bunch of things. So what do we do? So first, let's let, so earlier I had this inequality for mu sub t of r and h. In this theorem, we'll use this again actually in a few weeks, but let mu sub t of r be mu t of r comma r. Remember this function is 0 at radii less than r, and is 1 at radii bigger than r plus h, and so it goes, and so it looks like this. R plus h in this case is 2r. So this is the weight. Okay, and so then let's fix t bigger than 0. We know that we have these bounds on the second moment, which we didn't need any assumptions, almost no assumptions, just they needed the Lipschitz constant. So we know that the second moment of the vorticity at time t, the second moment, with respect to the center of mass, is bounded by e to the 2 lt times the second moment at time 0. Which is, so the second moment is the integral of the vorticity multiplied by x by distance squared root from the center of mass over 2, and that's always less than epsilon squared over 2. And so this is something like e to the 2 L capital T over 2 times epsilon squared if. Okay, so we have that, and so for example, all these estimates involving this thing, that's small. That's epsilon squared. Okay, and so, and let me just call this, so I don't know if I've probably been doing this without saying it, and this, you will have found this unsettling if you've never seen this before, but there's this analyst convention of just using C to denote any constant that could be computed in principle. And the unsettling thing is that the C may change from line to line, which it will do. And so again, I'll write C to mean, below I'll write C to mean something different. Here, C is 1/2 e to the 2 capital L capital T. But if we don't need to keep track of it, there's no point in wasting brain power on irrelevant details. So we'll just call it C. Okay, and so then what? And so then from this, we know that, say, well, also, so again, mt of r is the vorticity outside here, outside radius r, and we can see that mt of r is bigger than mu sub t of r, but it's smaller than mu sub t of r over 2. Which has this weight. And so I can replace this by mu sub t of r over 2. Okay, I've just made the right hand side bigger. And so mt of r, we have, so I'll just integrate this inequality, mu t of r is less than I guess u0 of r plus, and let's call it, say, kappa of r times the integral from 0 to t of mu t of t1 of r over 2 dt1, where kappa of r is this constant, c r l over h plus f infinity. And then here I have so this I is of order epsilon squared. Well, okay, times I, let's call it c epsilon squared over h r squared. I guess h is r, this is r cubed. R cubed, and then plus I over r to the fourth. Okay, some constant. Okay, so what I want to do is I'll take, so for r bigger than the square root of epsilon, some good things happen. So first of all, we can say that this kappa of r is just bounded by some constant, because and here h is r over 2. No, h is r, excuse me. Okay, and so this Lipschitz constant is a constant. My assumption that Elmstein-Nordbeth also, that's a constant. We have a epsilon squared over epsilon to the, so r cubed will be at most epsilon to the 3/2. R fourth is the most epsilon squared, and so I of omega. And so this whole thing is bounded by some constant, independent of epsilon, not the same constant as above. I'll just call it C because we don't need the details. That's one good thing that happens. Another good thing that happens is that the initial mu0 of r is 0, because we're looking at the vorticity outside the ball radius r, outside the ball radius greater than the square root of epsilon. But we know that initially the vorticity is contained in a ball radius epsilon around the center vorticity. And so this for sure is 0. And so then, for example, for a positive integer, say mu sub t of 2 to the k times the square root of epsilon, that's bigger than square root of epsilon, is less than, okay, I'm going to write this down. So this is 0 plus a constant, and let's not bother to write this. A constant times the integral from 0 to t of mu sub t1 of 2 to the k minus 1 square root of epsilon dt1. Okay, good. And so now let's just iterate. And this is a nice proof. I like this proof. This is due to Markio and probability. So I iterate k times, and I'll find that mu sub t of 2 to the k squared of epsilon is bounded by a constant to the k power, 0 to t, 0 to t1, etc. In the end, I'll have 0 to t sub k minus 1, mu sub t k of square root of epsilon dt1 up to dtk. Okay, and then, well, this mu again is it's the vorticity outside a certain region, and I think I divided by the total vorticity. But anyway, the vorticity outside a certain region is certainly bounded by the total vorticity, and since I divide by the total vorticity, this whole quantity is less than 1. And so then if I just do the integrals, I'll get c to the k, and I believe I get t to the k over k factorial. Okay, and now I want to use Stirling's formula, if I can remember Stirling's formula. And so that will give me, I believe, c to the k times t to the k times e to the k over k to the k plus 1/2. Okay, and so now what I want to do is I claim, well, let me choose, let's fix, let me tell you how I choose k. So let's fix, so remember the statement of the theorem contains a parameter alpha. Alpha is a number smaller than 1/2. And so I'm trying to contain the vorticity in a ball of radius epsilon to the alpha. Let's choose beta, who's between alpha and 1/2, and choose k such that, let's say, maybe 1/2 epsilon to the beta is less than this number, 2 to the k times the square root of epsilon, and which is less than epsilon to the beta. In other words, 2 to the k minus 1 is bigger than 1 over epsilon to the 1/2 minus beta is less than, I don't know, something. Okay, is less than who knows what. Okay, and so so then let me just take, this leads, I believe, to k being 1/2 minus beta times log of 1 over epsilon divided by log of 2, maybe minus 1. So k minus 1 is, sorry, this is a k plus 1, isn't it? K plus 1 is this ratio. Okay, and so then this is the k I will choose, and then that arranges the, and sorry, I want the integer part, excuse me. And so if I just chose k to be this number, I would be in this range, and by choosing the integer part, I get, I think this is right. Anyway, this is right up to a factor of, up to plus or minus 1. Okay, and so then my claim is that, so then I have this bound for, let's see if this is better. No, this isn't. No, is it better? Okay, I have this bound up here for mu sub t of this number whose order epsilon to beta, and here it is. And I've told you what k is. And my claim is that if epsilon is that this thing, as epsilon goes to 0, this converges to 0 faster than any power of epsilon. So, you know, this is, and so this is like some constant c, not a small constant times log 1 over epsilon. And so here we have, you know, some, it's bounded by, so t, little t is bigger than capital T. C naught log 1 over epsilon. And down here we have this, so I'm being a bit casual, but this is, okay, and so it's pretty easy to see that this goes to 0. Faster than epsilon to the gamma for any positive gamma. Okay, and so then we may choose. We may thus fix epsilon not bigger than 0. So given, say, gamma 1 positive, we can fix, say, epsilon not bigger than 0 such that, okay, so this is, this is the vorticity outside this number, which is bigger than the vorticity outside here. Not that it matters, but such that say mu t of epsilon to the beta is less than epsilon to the gamma for all. Okay, gamma 1. And so given any positive power, I can choose epsilon so small that in a ball the rate is a bit bigger than epsilon to 1/2. The vorticity outside there is less than epsilon to the gamma. I can make the vorticity outside a ball bigger than epsilon to 1/2 be an arbitrarily large power of epsilon. So essentially as small as I like on the scale of powers of epsilon. Okay, so then we're ready to finish the proof, I believe, if we can. So here's the strategy. So here's the picture so far. We have the center of vorticity, and we have a ball of size, a small ball, epsilon to the beta. And outside there, the vorticity is practically non-existent. Okay, and so what I'd like to do is the following. And so I'll make a good choice with this gamma 1 in a moment. So now I want to consider, so now, fix some alpha naught, or some alpha, let's call it, in the support of the vorticity times 0, which is in this ball of radius epsilon around the initial center of vorticity. Okay, and then let me consider the trajectory from here. So let's let x of alpha t solve as usual. Well, okay, not quite as usual. Dx dt is u plus f of x and t, and x of alpha 0 is alpha. Okay, so I consider a trajectory who starts inside the support of vorticity, and I know that the vorticity at every later time will be contained in the union of all these trajectories. And so if I can control what those are doing, if I can control how far those stray from the center of vorticity, then I will have proved my theorem. I will have shown that the vorticity at later time remains contained close to the center of vorticity. Okay, that's my goal. And so let me define, let say rho of t be the, let's say, I'll write x of t without exhibiting the alpha, x of t minus the center of vorticity, the distance from the center of vorticity. And I don't want to worry about if it gets too close to the, maybe 2 epsilon beta, if it's too close. And so I only care what's happening if it strays rather far. And so my claim is that for, I want to get a differential inequality for this. So for almost every t, this rho prime of t is less than some constant times, well, the L infinity norm and the W11 norm. and then rho of t. So norms of the vector field, the W infinity norm. Okay, this is my claim. And okay, and we'll use again the lemmas we proved a few days ago. Okay, and so this should follow from, well, okay, so here's what we'll do. Here's a picture. Here's the center of vorticity. And we have this point out here, x at time t. And we'll just compute. Well, so there are two cases. So note if, well, let's say rho prime of t is 0 almost everywhere on the set where rho of t is equal to epsilon of the beta, it's minimum, or 2 epsilon of the beta. Right, and so if this happens on a set of positive measure, then rho prime of t vanishes on that set. Okay, that's the basic analysis. And so let's then consider. So let's assume. Okay, so rho was either this or that. We've ruled out the second case, and so let's assume that. Rho of t is equal to this x of t minus this center of vorticity. And that's bigger than 2 epsilon to the beta. And let me just differentiate that. And I need space, so I'll go down here. Rho prime is, well, I'll have x minus p epsilon over x minus p epsilon Euclidean norm. And then I take the dot product with d dt of x minus p epsilon. And this is exactly x minus p epsilon over. And then this is, so dx dt is by definition u plus f. And then again, dp epsilon dt we've seen several times is the integral of f of y t omega y t d y. Okay, and so that's what I have to estimate. And my 3 lemmas up here will help me do this. So first, let's handle, let's do this piece. And let's just look at lemma 3. And this piece, and lemma 3 immediately gives us a bound for this. So, so we can see what, so in the second term, I have a dangerous x minus p in the denominator. However, x minus p is bigger than epsilon to the 2 beta. 2 epsilon to the beta. And so this denominator is at most epsilon to the minus 2 beta. On the other hand, I have epsilon squared in the numerator. And so this is less than, from the second term, I'll get f infinity times epsilon to the 2 minus 2 beta, no problem. From the other term I have, well, that'll give me a constant times constant times rho, right? The Lipschitz norm L times a rho times a constant. Okay, and then this is say less than constant times epsilon to the beta. You see here in my claim, on the right-hand side, I have a rho of t who's at least epsilon to the beta, and so any constant terms who are smaller than epsilon to the beta I can absorb into here, and epsilon to the 2 minus 2 beta should be smaller than epsilon to the beta if I've done this correctly. Yeah, that's right. Okay, good. And so this term is okay. The other term, well, our lemma, we'll use the other two lemmas. So x minus p epsilon over x minus p epsilon dot u is, well, I use the Jerrard kernel to rewrite u, which is an integral over omega of x minus y per over x minus y squared. And I divide them into two pieces. I divide into a piece who is near the vortex and a piece near the center and a piece who's far from the center. And so I'll get a x minus p epsilon over. And so near will be, say, I look at the ball of radius rho over 2, where rho is this, rho of t over 2. And then I have x minus y perp over x minus y squared. I need a factor of 2 pi. And then an omega of y dy. And then I have the same thing with the integral over the ball of radius rho over 2, the complement. Okay, and then my remaining two lemmas, oops, I need more space. My remaining two lemmas will help with this. Okay, so so the first piece we can see has exactly the form from lemma 2. Here was lemma 2. And it has exactly this form. And so here our assumption was that h is less than, so r was the distance from, so in this lemma, we're applying with r equal to rho. R was the distance of x from the center of, this should be the center of vorticity, excuse me, for mistakes. X minus p epsilon is rho, and we're taking h to be a rho of 2. So this condition is satisfied, and we get this estimate, which is exactly consistent with, so here we have epsilon squared over over something of order epsilon to the 3 beta, and that's some positive power of epsilon. So this contribution is, for us, will be less than epsilon to the 2 minus 3 beta times a constant. And that's, which is less than epsilon to the beta. Okay, and then for this one, we haven't used lemma 1 yet. So lemma 1 is the remaining thing. This was the first thing we proved. And this says, we look at the convolution of the Jerrard kernel with the vorticity. And here, so I want to apply this, I'm applying this to the part of the vorticity living outside the ball of radius rho over 2. Right, and which is at least epsilon to the beta. Okay, and we've arranged that outside that the amount of vorticity living outside that ball is of order epsilon to the gamma 1, where gamma 1 is something we can choose. We can make it as small as I like. So by lemma 1, and so this will be less than, say, m sub t of rho over 2. That's the L1 norm of the vorticity to some power. And then the other part was the LP norm. And so the LP norm, we don't know where it's concentrated. We can just say the omega, but we know it's preserved by the flow. And so this is for some theta, it doesn't really matter very much which. And this is, say, epsilon to the gamma 1. So that's what we did up here. We arranged that the amount of vorticity outside the ball of radius epsilon to beta is this power, is this, we can make it as small as we like in terms of powers of epsilon. Okay, so this is epsilon to the gamma 1 to the theta. And this is, and this by assumption was epsilon to the minus gamma to the 1 minus theta. Okay, and so then by, and we can make this all be less than, say, epsilon to the beta by choosing gamma 1 large enough. Okay, and so so we have this picture, the vorticity inside here. We use this one lemma to control its contribution, and then outside that there's basically nothing, and so it contributes basically 0 to the velocity. And let me emphasize this lemma 2, which was somehow the crucial thing. In fact, the velocity is generated the vortices are big, but the radial component is small. So lemma 2 is really the crucial thing. And this says that although the velocity generated by this concentration of vortices is large, the rotational component, the outward radial component is something we can control. Okay, and so that so I think we proved the claim. So we have either things who are multiplied by rho, or things who are smaller than epsilon to the beta and hence can be absorbed into the constant times 1 times rho. Okay, so this is done. And then once we have the claim, we can then use Grunwald's inequality. We know also that rho of 0 is 2 epsilon to the beta. Rho is the distance, was the smaller of the distance from this point in the support to the center vorticity and to the beta, and this shows that it was the I said min, I should have said max. I'm sorry. Hey guys, ask questions if I said anything crazy. Okay, so where did I define rho? Okay, max. I want to be the larger. And okay, so sorry about that. Okay, and so the point is that initially, because we're considering point in the support of vorticity, this is initially of order epsilon, and so the larger of these two is the epsilon of the beta. And so so we have this rho who grows, so it'll grow exponentially with this constant, and so let's just call this a constant c. Okay, it depends on f, but it's a constant c. And so the conclusion is rho of t will be bounded by e to the c t times 2 epsilon to the beta for 0 less than little t less than capital T. Okay, and this will be less than, say, epsilon to the alpha if epsilon is small enough. Okay, and so what we've shown is that any point in the supported initial vorticity strays at most epsilon, strays less than epsilon to the alpha from the center vortices at later times, at any time in this time interval from 0 to capital T. And since the support of omega at time t is the set of points x of t alpha, where alpha is in the support of the initial vorticity. This proves the theorem, right? So the theorem was, here it was, every point in the support of the vorticity time t is at most epsilon of the alpha distance from the center vorticity time t. And that's what we've shown. Okay, and so nice theorem, nice proof. And it rests on this careful computation of the radial component, the outward radial component of the velocity field generated by a vorticity in a small ball. And then finally, we won't finish this today, unfortunately, but with, I want to go back. So what remains is our original interest was this problem of, not the background flow, but the actual Euler equation where my initial data has some number m of blobs of concentrated vorticity. And so here was the setup. To remind you, we'll have to do this next not on Monday, because Monday is a holiday on Wednesday. We fix some parameters, some vorticity strengths. We fix a solution of the point vortex system of ODEs, and then we solve that, and we want to show that we want to consider initial data for the Euler equation, who looks like a bunch of delta functions with masses gamma located at these points. In other words, whose concentration balls rates epsilon on the initial points. And we assume that if the vorticity gamma m is positive, then the vorticity in m flaw is negative, and vice versa. Sorry, it's positive. And if the vorticity doesn't change sign within any of these balls. Okay, and so here's the same assumption. Unfortunately, I've changed all the constants here. I'll try to fix this. So this alpha is what I called gamma before. Let's change it. So we assume that some LP1 for some p bigger than 2 grows like some negative, is bounded by some negative power of epsilon. And then we look at, so remember T star, it's possible that this ODE system has a finite time collision. And so if that happens, T star is that collision, otherwise T star is plus infinity. We fix any time before such that there's no collision up to time capital T. And so beta here replaces the role of alpha from the previous theorem. And the claim is that for sufficiently small epsilon, there are trajectories, these p m epsilons, such that for every time t in this interval up to capital T, the support of omega epsilon is contained in the ball of radius epsilon of the alpha around these approximate trajectories. And these trajectories stay close to the ones given by the point vortex ODE. Okay, and so we'll have to do that next time, but this will turn out to be a pretty easy corollary of what we've done, which is to analyze the system of Euler with the given background in considerable detail. So both to control the dynamics, we have control of the growth of the second moment and the distance from the distance of the center of vorticity from the ODE trajectory, and the growth of the size of the diameter of the vortex blob. And so we'll have to wait and do that next time.